All right, so Lab 3 involves three different parts. The first part of Lab 3 involves modeling exponential growth in Excel. The second part involves modeling exponential growth in R, and the third part involves modeling exponential growth in Insight Maker. In this short video, we will go over getting started with modeling exponential growth in Excel. Now, I'm actually going to use two different tools, one being Google Sheets and one being Excel. They're very similar functionality and just a couple minor differences. So I will go through both. I'll start off with Google Sheets actually, and the lab instructions tell you to download this template file to get started, which you're welcome to do now, but I'm going to start from scratch in Google Sheets. There's not that much in this, so it doesn't take long to create this sheet from scratch. So that's what we'll do right here. So what we want to do is model abundance over time. So I'm going to start off by making a column for time, which is representing years in this case. I'll start off at year 0, and we will move on to year 1, and we'll go all the way to year 30. So I'm going to just drag this down till we get to year 30. Oops, and one more. There we go. So I have 30 years now. So that's just a start. So I know how many years I want to model. And the second column here is just going to be abundance. And abundance is typically represented as N. So I'll just call it N in the column header here. So my initial population size here will be 100, and that will be representing the abundance at year 0. And what we're going to be doing is modeling the abundance at year 1 and the abundance at year 2 all the way down to year 30. So that's where we're going. But before we can do that, we first want to define the intrinsic rate of growth, R. And so R is the intrinsic rate of growth. And I will also mention that the way we're thinking about R right now, it is the discrete version of R. So the way I represented it in the opening lecture and in the top of the web page is R sub D for R discrete. So this is the intrinsic rate of growth, and I'll just write down discrete here so that it is very clear what we're doing right now. All right, so we have intrinsic rate of growth, and that will be 0.1. I don't need that to be bold there. Okay, so now we have everything we need. So we have the initial population size, we know the number of years we want to model, and we have the intrinsic rate of growth. I'm going to, since we're talking about discrete population growth right now, I'm going to convert this into lambda, which we more typically talk about lambda as the kind of multiplicative rate of population growth when we're talking about discrete population growth. So lambda is just equal to, I'll just use the equal sign here to define that I'm entering an equation here, and it's just equal to 1 plus the discrete intrinsic rate of growth. So lambda in this case is 1.1. Both of these just represent 10% annual population growth. When I'm defining it this way, I'm just saying, okay, what percent growth rate am I talking about? Well, I'm talking about 0.1 or 10% growth. With lambda, I'm talking about what number do I need to multiply the previous year's abundance by to get the current year's abundance. And that is 1.1 to represent, you multiply something by 1.1 and that you get 10% growth, right? So really these are representing the exact same thing, just in a slightly different way. One is called R, one is called lambda. All right, so now we have everything we need to get started. If you return to the lecture page, you'll see that we are going to now be applying this fundamental equation of exponential growth, which is represented as equation 16 here in the lab. It's just the abundance at time t plus 1 is equal to lambda times the abundance at time t. Or alternatively, we could represent this as the abundance at time t plus 1 is equal to the abundance at time t times lambda. Either way, obviously. So let's go back to the spreadsheet and we can implement this model. So we'll use an equal sign here to represent that we're just about to enter an equation. So the abundance at time 1 is equal to the abundance at the previous time step, right, times lambda, right? And if I just hit enter, then I get a 10% population increase at time 1 or year 1, all right? And now what I want to do is instead of doing this, I could just keep on going and say, okay, the abundance at time 2 is equal to the abundance at time 1 times lambda. And I could just keep going on and on like that. But there's an easier way in Excel and in Google Sheets. So all we have to do is just copy this down all the way. And oops, that didn't quite work. And you'll see that what we did do is copy down a formula just by, I should have mentioned, all I did here is I just double clicked right in this lower right hand corner of the cell. Another way to do it is just to drag down. So either way works. If you double click, it'll guess how far you want to drag down, and in this case it knows because I had 30 years here, it just knew to automatically drag down all the way to year 30. But if you want to be really explicit, you could drag this formula down, all right? But something's not quite right here, obviously, because 0 doesn't represent a 10% increase in population size from 121. What happened here? Well, you see that if you look at this formula here, I'm referencing the previous year's abundance times lambda, right? Previous year's abundance is in cell B2, lambda is in cell G3, all right? And here, again, I'm referencing the previous year's abundance and lambda, right? Lambda's in cell G3, previous year abundance in cell B3. Now, what am I doing? When I drag down the formula, now it's referencing correctly the previous year abundance of 121, but now it's referencing a blank cell, cell G4, because by dragging that formula down, Excel or Google Sheets is automatically going to think that I want to drag any references down with it. So if I want to stop that from happening, so I can go back to this initial one, and I want to keep this formula to reference this lambda, which is in row 3. It's always in row 3, right? I want to fix it at row 3. I can just use a $ before the 3. That fixes the reference to be referring to the third row at all times. And then if I copy this or drag this down like that, then I do get a exponential growth all the way. So 121 is 10% increase over 110, 133 is a 10% increase over 121, so on and so forth. And by year 30, I am at a population size of 1,745. So let's visualize this increase. It should look like exponential growth if we plot it out. So I'm going to highlight, I'm shift clicking on this cell here to highlight this cell. So I first clicked at the very top left-hand corner of the area that I want to highlight, and then I'm shift clicking at the lower right-hand corner, and that highlights the whole thing. And now I can add a chart here. So I'm going to add a chart, and it will automatically give me this kind of nice chart with time on the x-axis and abundance on the y-axis, just the way we'd like it. And you can see what looks like exponential growth, right? So that's pretty much just getting started with exponential growth in spreadsheets. that's really all we need to do right now. You're going to go a bit further in Lab 1, but I would like you to try to do it on your own, and then we can work with you if you have any questions. I could, of course, go farther here, and it would be relatively easy to plot exponential growth all the way to, year, oops, didn't do that right, all the way to year, say, 50, right? And just get rid of those extra 30s there. And all I have to do then is just drag this down all the way, right? And I can highlight, let me highlight from the very top, and highlight this and just insert a chart. And now we have a chart of exponential growth all the way to year 50, and we see that we're now at an abundance of 11,739, and we're starting to get a sense of the power of exponential growth here, that only in a few short years, 50 years, okay, maybe not that short years, but the population has expanded from 100 all the way to almost 12,000, and all we're doing is increasing the population by 10% each year. So exponential growth, again, that's what it does. The faster it grows, the bigger the population is, and the bigger the population is, the faster it grows. So that's all I wanted to do with Google Sheets. Let's quickly do the same thing with Excel, just to make sure everyone is on the same page, and whatever tool you're using, you are good to go. So here we are with Excel. This is the template that you can download. If you go to the website and you just go to this very first exponential growth in Excel, you can download this template sheet to get started. So this is where you can start. I already made a column for time for you, and I gave you a starting abundance and the per capita rate of growth. And again, just like we did before, what we can do is first make lambda. I will make that equal to 1 plus the per capita rate of growth. Looks something like that. So now I have my constant multiplicative rate of growth, lambda. I have the initial abundance, and I know how many years I want to simulate. So let's get started. I'll put a equal sign here, take the previous abundance, multiply it by lambda, but I'll fix that reference so that it's always referring to the row 5, even when I fill this down, and it gives me a final abundance of 1745, just like we had before, but now it's giving us fractional individuals. We don't really like that. So I'm just right clicking on the column to reformat. I'm going to go to the number format here, and I'll just reduce the decimal places to 0 so that now I have whole individuals, which obviously makes me feel a lot better than fractional individuals in a population. And now we have the same numbers. We should anyway have the same numbers that we had in our Excel document. Sorry, in our, this went to year 30, 1745 and year 30, just like we have, this is the Google Sheets obviously, and now this is Excel, and we get the same number. And the last step was just to plot this out on a line plot or scatter plot. So first of all, let's do the same thing. We'll just click on the top cell here. I'll shift click on the bottom right hand cell, and let's insert a plot, a chart, and I'll insert a line chart here. I'll just use this option. Your Excel might look a little different than mine, so it might take you a second just to find where things are. This plot doesn't look quite as nice because we don't have labels on the x-axis and y-axis, and we have kind of a useless title for the plot. So I'm just going to get rid of this title, and in fact I'll just add axis labels. I'll add both the vertical and horizontal axis labels, and I will use this, I'll fill this in. So this represents time in years, right? And this axis represents abundance. And I think we're pretty good to go. So that's exponential growth. Again, if we wanted to, we could fill these down further and plot exponential growth for 50 years or whatever. So there's a lot of places we can go from here, but I think I will end here and let you work through lab 1. So good luck with lab 1, part 1, and I'll make a video to get you started, a similar video to get you started with R. Have fun, and I'll see you in lab.